lecture 2 of module 5, we looked into transportation of concrete bearing one technique, that is pumping. Pumping we just mentioned there, pumping of concrete. Pumping is more versatile than most of the methods, because it can pump horizontally as well as vertically. But when I am looking at pumping, I should also look at pumpability, and which is linked to workability, which we have not discussed so far. So, we will discuss about workability, particularly the empirical measures of workability in this lecture, followed by pumping. So, we will talk about empirical tests and then we will talk about pumping. Right. So, let us look at what is workability of fresh concrete. One definition is the amount of useful internal work necessary to produce full compaction. It should be workable, that means I should be able to make, as we discussed earlier, we said that relatively not self compacting type, relatively less flowing concrete, normal concrete as we have been using over years together. Initially when you put the concrete, it forms a heap, like the soil does, and you have got an angle of repose. So, particles are supported by other particles and it forms a heap sort of, right, maybe more flowing than soil, but it forms a kind of heap, and there is as much as 30% voids, and this 30% voids we drive off by compaction, usually through vibration. Engineered compaction will be through vibration. Of course, the extreme case where you do not need vibration is the self compacting concrete, which I mentioned earlier. So, therefore, the workability is defined as the amount of useful work required to produce full compaction, and we also said that it does not conform, seldom conforms to the shape of the mold. Therefore, there is some amount of mobility is also involved. So, workability is the useful internal work necessary to produce full compaction. Now, useful internal work is a property of the concrete alone, although some amount of energy might be spent in overcoming the friction of concrete and formwork, etc., or rebar and so on. So, this is what we define workability as, and it has then three components, because what we are doing, it would be in a heap, it has to move, and we have to drive out the air. At the same time, it must maintain its cohesion. In other words, relative materials should not get separated from each other. So, the three components can be written as compactability, that is, we should be driving out the air, and the work done is to drive out the air would involve some amount of movement and flow. So, if you recall the rheology of concrete which you talked about, we talked about yield shear stress, and beyond which I have some viscosity, and therefore, the stress at any point will be given by this yield shear stress. This is your yield shear stress, plus coefficient of viscosity and a normal force, which will be a function of normal force, So, stress like shear, like soil. If we do box shear test, we would see that the amount of stress strain curve is a function of the normal stress that we apply, the shear stress it can resist, and mu is a kind of coefficient of friction or viscosity, dynamic, it is plastic viscosity. So, stress would be this, and this is the strain, shear strain. So, half shear stress into strain, we know the strain energy, that is the kind of work done. So, that is the kind of strain energy that the material will absorb. So, that is the amount of work done. So, compactability is a function of the work done, which is half stress into strain, and stress is yield shear stress plus the viscosity, and if you have applied any normal stress. We will come to this sometime in the next lecture when we talk of compaction a little bit more, and this is a strain. So, therefore, this is a function of the work done, which is given as the strain energy, which is half shear stress multiplied by the strain, half shear stress multiplied by the strain, right. So, that is it. This is compactability. So, this is how easily you can compact. So, there is the energy required to actually cause some movement, some shear stresses, shear strain, and that results in compaction. Mobility is a flow. So, I should be able to drive out the air, and that is compactability, and if I want to drive out the air, there should be shear, the shear, it should show a Bingham kind of behavior. I should cross the yield shear stress, and then it flows and then occupies most of the volume. So, that occupies the volume and air moves out. So, therefore, that is related to work done. The mobility is a function of, it is the flow, because we said it does not conform to the mold. Therefore, there has to be some amount of movement to attain the shape, and this mobility is a function of mu again. Mu is a viscosity, tau 0 is again yield shear stress, and of course, it is a function of the maximum size of the aggregate, maximum MSA, because larger one will easily move, the smaller one moves less. So, workability actually has got, so far we have seen two components. I said I should be able to compact it very easily, and it should attain the shape, and lastly the particles should not separate out from each other, and that is basically a kind of stability or function of the tensile strength of the fresh concrete. So, compactability, mobility and stability, these three ensures that it will not segregate, it will remain same cohesive as it was, and then it will move to the and it will be mobile to attain the shape of the mold, and I should be able to drive out. So, the least work required would give me better workability, least energy I require. So, internal work required should be least, and therefore, work required should be least. So, easily flowable one, it should be more flowable, and that is what it is. Now, these are the concept of workability. Now, you see, if I want to from fundamental principle, if I want to come to compactability, mobility, stability, and generate a kinds of workability function, that would be fairly complicated, because I would need tau 0, I would need mu, sigma, and that too as a function of mixed parameters, concrete mixed parameters such as cement content, water cement ratio, etc., etc. All those, I mean, water content, paste content, and so many factors could be there. So, from fundamentals to relate to those factors, particularly mixed proportion, that is content, water content, cement content, aggregate content, coarse aggregate content, MSA, maximum size of aggregate, and any other admixture content, and so on and so forth. Relate this to tau 0 mu is not yet, we have not arrived at that kind of understanding till today as far as concrete science is concerned. So, we have to, but then we need some measure for workability, and that is, we needed it for last 30, 40 years or 50 years or nearly 100 years for which concrete is being used. So, therefore, some empirical tests were developed. For comparing the workability of different concrete. Now, to both, there are a number of tests actually developed, and each test measures a thing. It does not measure all three components, all right. It does not measure all three components. So, relative comparison of different mixes as far as their workability is concerned, that is possible, but absolute from fundamental principles we are yet to arrive at that understanding. So, therefore, we rely on some empirical tests, all right, empirical tests. Although some work has been done in 1950s onwards, and even currently there is a lot of work done on rheology, particularly related to flowing concrete. However, for normal concrete we need some empirical measures, and these measures are like Slump, BB, compaction factor test, which are more popular. There are number series of other tests, and yield stress and plastic viscosity will be rheological test. Actually, at the moment we are not looking at them, and air content, pumpability, density, some are specific tests related to fresh concrete. Okay, we are not interested, but today we are interested more in Slump, BB and compaction factor test, which are very common empirical tests which are used. In fact, this is most common. This is most common. This is used for drier concrete, and this can be used for some concrete which are in between, but this, for example, fiber reinforced concrete, one would prefer this test, because where workability is very low, or roller compacted concrete, which is actually compacted by road rollers, earth moving machineries. There we do BB test with some modification, put a surcharge on top, because it is 0 slump, practically no slump you will get it. So, we will come to those tests, and these values of, let us say, slump or BB time or compaction factor value, this depends upon the section dimension, amount of reinforcement, etc., how much is required, that will, So, most of the normal strength concrete, one would specify the slump, sometime of course BB, a few of the practices might even include compaction factor. There are some other tests, but we are not interested. These three are the most common tests. So, let us see what these tests are. For example, slump test, it was actually devised by D. A. Abraham. It is Abraham slump cone, and it is very simple. You place the concrete, pack the concrete here in a cone, which is dimensions are given 200 and 100. So, 2 is to 1 is 2 is to 1 is this, and this is 300. So, this is a cone, truncated cone, and you pack the concrete in 3 layers, compact it in a standard manner, lift this up, the cone up. Now, concretes attain some kind of a shape like this after lifting up. Now, this difference is right from the top is British and European standard, tells you the slump. American standard takes the bottommost one, and one can take average. So, original height depression, depression is what you are interested in. So, depression from this level to how much is the depression, that is called the slump, that is called the slump, that is called the slump, right. So, slump is measured using upturned cone and slump rod as a guide. So, this is the rod you put it, and it is as a guide, and so therefore, this is the slump. So, we can understand that if the concrete is flowing, then slump will be very high, if it is stiff, slump will be very low. So, you can in fact classify, this is true slump, something like shear slump, this it is just simply sheared off, and collapse slump, which is actually flat. Normally, higher the slump, flowing concrete will show this kind of a collapse behavior. Most of the ordinary concrete, of the good old days, normal concrete would show this kind of true slump. So, this is one test. Compaction factor is other test, where you have a hopper in which you fill the concrete in 3 layers. There is a gate here which you can open. So, you open it, the concrete just goes there, it is closed now. So, there is a kind of standard compaction you have achieved here by a drop, drop from upper hopper to the lower hopper. So, this is about a meter height. So, there is a standard compaction you have achieved. So, that if somebody might pack it in a different manner, it may depend from individual person to person. So, there is a standard, there is a drop, through this drop you have got a standard, some compaction you have achieved, and which will be more or less similar by it will not be as much as individual dependent had this been not there. Then you drop the concrete into a cylinder, standard cylinder, which is 150 mm dia by 300 mm height, and it will excess concrete you travel it off from here. So, excess concrete travel it off and find out the mass of the concrete. So, find out the mass of the concrete, find out the mass of the concrete. So, mass of the concrete as difference of cylinder plus concrete minus W cylinder. So, you find out difference, this is the mass of the concrete. Now, the volume is known, or next what you can do, you can take this cylinder, put in more concrete and then compact it in a standard manner. So, compact it in a standard manner, let us say and then you will get this after drop. So, this is let us say this one is W1, and then similarly you compact it in a standard manner, fill it in and compact it in a standard manner on a vibrating table, and then you get W2 is equals to W cylinder plus concrete vibration, right, minus W cylinder. So, W2 divided W1 divided by W2 is we call as compaction factor. W1 divided by W2 we call as compaction factor. So, therefore, what we are doing? We are actually measuring concrete, trying to find out by this standard drop the compaction of the concrete or the mass we attain by compaction divided by. So, it is the ratio of the mass we attain by dropping it through a kind of a standardized compaction divided by full compaction under vibration in a vibrating table. This ratio we call as compaction factor. So, higher this value, the ease of it is easier to do the it is more workable the concrete is. For example, if it is water, it will be simply water 1. If it is a flowing concrete, it will be simply 1. It will be simply 1. So, how easily it gets compacted, that is what it is. How it is easily it drives out the air, that is what is seen. So, it is in fact a function of compactability, while slump is actually settlement under its self weight. So, depend a little bit on flow properties, under self weight how much it settles. So, basically will depend upon actually angle of repose also, it will depend upon angle of repose also. A stiff concrete will have high angle of repose, while flowing concrete will have, so somewhat related to flow, but this can be related to actually compactability. So, compaction factor mostly maximum can be 1, but it is never 1, it is more than about 0.65, 66 or 0.7 to about 0.85 or 0.9. So, compaction factor is like that, So, this is another empirical measures. It is a more suitable for laboratory situation, not field application, of course, not very easy. BB test is the other test where it is actually a variation of remolding test. So, originally what was done was you have the slump cone, the concrete, and then remove the slump cone. Concrete might attain a shape like this, right, because there will be some settlement, and then you put a piston here. In this case, of course, clear prospect disc piston sort of a thing, it is a disc basically, and from this now there can be some weight here and you vibrate it, then it attains the cylindrical shape. So, 300 mm cylindrical shape, this cylindrical shape. So, as soon as cylindrical shape is obtained, the one can put off the stopwatch, you start the vibration in a standard manner, and as soon as it attains a cylindrical shape from this truncated cone shape or slumped from a truncated cone shape, then to this time is measured. This is called VB time. Originally remolding test was done to find out the effort required to change from this shape to this shape. So, truncated cone shape to so original remolding test, it is called remolding test. So, effort required for remolding test original remolding test. So, the effort required to remold it from this truncated shape to a cylindrical shape, that is called remolding test, but now of course, it is measured in terms of time. So, and we call it VB time. So, this is actually higher the time, more effort you require. So, less workable the concrete is, lesser the time, least effort you require. So, therefore, VB test is related to this. Now, it is good for stiff concrete, because stiff concrete will take longer time to attain that shape, whereas the flowing concrete will quickly attain the shape, and therefore, it may not be easy to measure it. All right. So, this is PV test, this is VB test, and it gives you an kind of a kind of a measure of moldability, because you are doing a remolding test. So, the time required from remolding from a given shape of truncated to slumped, truncated cone shape to a cylindrical shape, how much time does it require. So, therefore, time required for remolding with a constant effort, all right. So, it is actually moldability, molding to a new shape, that is what it talks about, and relates somewhat to mobility, relates somewhat to mobility. Stability is the tensile is related to tensile strength of the fresh concrete, right. Stability is related, so it should not separate out. All right, if we compare these three tests, we will see that here is a compaction factor, on this side is a VB time, and here is the slump. So, compaction factor varying from about 0.6 to 1, and this side is a slump. So, when it is very close to, it is going towards near to 1, very high compaction factor means slump is also very, very high. But the sensitivity of the compaction factor to lower VB time, So, this is, I mean, the VB time is less VB time here, lower VB time, it is not very sensitive. If you look from between slump and the VB time, higher slump you have very less VB time is very less for high slip. So, it is not, VB time is not sensitive to high slump concrete, but it is very sensitive for low slump concrete. So, when you have slump 20, the VB time change will be quite significant. So, VB time is good for stiff concrete, slump is good for relatively flowing concrete. Stiff concrete it can't handle, because if you look at the slump here, for the stiffer where VB time is changing, the slump does not change much, right. So, it also depends upon aggregate cement ratio, etc., etc. Compaction factor is somewhat in between. If the compaction factor change for high slump is very little, it is not changing, and here also for a stiff concrete it is not changing, but it changed significantly in this zone where you have got relatively low slump and possibly relatively slow VB time as well, relatively slow, it actually is relatively slow, this is a slump, and the compaction factor is in between, it's somewhere in between. Compaction factor, so for example, this slump 20 to 40 slump compaction factor is good, or even 50, 60, 80 slump it is quite good. But if you go to 0 to 20 slump, its change is very little. So, correspondingly if you see 20 to about 80 slump, this zone compaction factor is still good compaction, and correspond to about VB time of 2 to 4 seconds and so on and so forth. So, therefore, what we find for stiff concrete VB time is good, for flowing concrete slump is good, compaction factor is somewhat in between. So, you can compare one with the other, one with the one, compaction factor is compaction factor only, cannot mix it up. So, the required workability is usually specified either in terms of any one of them. Most popular is of course slump, because of its simplicity and ease of performing the test at site, right. VB is required where you are doing very stiff concrete, such I gave an example, for example, fiber enforced concrete. Introduction of fiber depending upon their L by D ratio, this workability gets reduced, because it is a kind of elongated, extremely elongated aggregate you are introducing. So, they actually disturbs the workability, they tend to become stiff concrete. Now, such concrete you can't measure with slump, because you will not get any slump variation, but compaction VB time variation you will get it. Okay. Similarly, self compacting concrete, there is no question of using VB time, or pumpable concrete, no question of using VB time, not even compaction factor. So, it will be slump and similar kind of thing. So, that is how we compare, that is how we compare different tests. If you see the slumps, you can have concrete today, you can have nearly 0 slump concrete to flowing concrete, which is self compacting concrete, right, self compacting concrete. So, there we talk in terms of slump flow. For example, you just lift it up, the slump cone, lift it up, and the spread of the concrete we measure. So, as you lift it up, the concrete will get spreaded along this direction, and you can see that the slump flow is measured. So, you see the extension of the slump is in this term, in this this kind of this kind of test called slum flow. So, concrete is very versatile, going from zero slump, roller compacted concrete to self compacting concrete. And I also talked about mini slump earlier. If you remember, we talked of mini slump test in the context of admixture compatibility or selection of admixture, etc. Mini slump test for paste, right. So, that is actually that is essentially related to the empirical methods for workability. As you can understand, pumping of concrete, pumping will be related largely to the slump finally. Okay, you can't do the other one. But anyway, let us see pumping of concrete, issues involved. First of all, let us see how what are the pumps types a little bit, and then we will go to pumpability of concrete itself, and then mechanisms and so on and so forth. Now, remember, any concrete cannot be pumped. Pumpable concrete is somewhat different than the normal concrete, because only thing that can be pumped in the only thing in concrete that can be pumped is water. Well, paste also you can pump, but that is because there is water present. So, as the water moves, it takes the other materials with it, and but then it should not go alone, leaving the solid behind. So, it should carry all the materials together with it, and therefore, concrete pumping, water is the one which is actually pumpable, and the solid should be in such a manner that there is no separation of water from the same, water from the rest of it. So, therefore, pumpable concrete can be just not simply normal concrete proportioning. You might have to proportion them a little bit carefully, so that pumpable it remains pumpable, right. Okay. So, pumping is used both transporting and placing of concrete. You can place straight away onto the mold, and then it combines both vertical and horizontal transport in one. Therefore, it is very versatile, and as I was mentioning, a pump together with let us say ready mix concrete truck, agitator truck coming, or the transit mixer coming and delivering your concrete, and straight away into the hopper of the pump, and from the pump straight away concrete goes to the mold, straight away it can go to the mold. So, quite a bit of advantage. Can place concrete in congested site with little excess otherwise, and you can place actually small or large quantities of concrete in the form continuously at a very fast rate. So, speed is also very high. It requires use of mix having special properties suited to pumping itself. That is what I was mentioning. It is just not, I mean, people, you just simply should not be thinking that concrete with a given slump, high slump, is just pumpable. Well, high slump is a thing, but that is not necessarily the sufficient condition for pumping. So, one has to see, because pipe might get choked. If the concrete is not proper, pipe might get choked, and more frequently it might get choked, because water may just flow leaving the material alone. Pumping rates ranges up to 75 cubic meter per hour or more. It will depend, current pumps might do much higher, and you can pump concrete to a distance of 90 to 300 meter horizontally. Maybe modern pumps might be even doing better, and it can be pumped from 30 to 90 meter vertically, but both you cannot realize together. So, either vertically up, if it is other maximum, for example, 390 meter may not be realized simultaneously, you will realize it somewhat in between. Types of pump. Now, most commonly used pump is reciprocating type. There are other types of pumps, but I have not discussed them actually, and this is simply mechanically driven. This is simply mechanically driven, as you can see, it is simply mechanically driven. You have a reciprocating engine, the piston is here, right, the piston is here, and it is in a suction stroke. So, you have a hopper on which concrete comes in, and you can see there is a valve, the circular valve. Now, it is open, the gate is open. So, concrete can come in. So, it is a suction stroke, and this there is another valve, actually it is closed, actually nearly closed, and the stroke is along this direction. So, it is a suction stroke stroking is along this direction. So, this is rotating along this direction, suction stroke, and as the suction occurs, this gate is open, concrete comes in and fills in this space. Now, the piston goes, then in the delivery stroke, as this rotates here, delivery stroke piston will go somewhere there, and simultaneously this valve will come and close this portion, and this valve will open up, this concrete portion will get aligned. So, it will be something like this, it will get aligned, and during the delivery stroke concrete will move out of the pump. So, it is basically reciprocating action, and this is directly mechanical, but this system can be modified to hydraulic system, and that is what is most commonly used. That is what is most commonly used, that is what is most commonly used. So, generally you will have this is a hydraulic system. So, this is hydraulic. Now, the same piston is operating, but it is operating hydraulically. That means, your fluid is the one which gives the pressure, and therefore, you will not have jerks. And now, there are twin valves, because twin pumps, you can see 1 and 2. There are twin pumps 1 and 2. There are two of them actually. So, what happens is, this is a common hopper, and the valve is such, the valves are such that while this is in suction stroke, this let us say this is in suction, the other will be in delivery. So, one of them is in suction, the other one is in delivery, and this is a hopper for collection of concrete, So, one twin pump, one in suction, other delivery. Now, normally what will happen, since it is reciprocating pump, if I plot the pressure for a single pump, pressure will be like this, delivery stroke in the pipe, pressure in the pipe will be like this. Then this is a suction stroke, there will be no pressure, no delivery side, there will be no delivery. Then it will be something, this will be another one. So, it is this pressure at the pipe, pressure with time, this side is time, pressure with time. So, if I have only one pump, this will be the kind of half rectified wave. But if I have two pumps like this twin pump, then I will have pressure in the delivery, pipe, the pressure will be like this. So, concrete flow will be now a full wave rectification actually. So, you will have something like this. So, twin pumps are what is most commonly used, and they are usually hydraulically driven. They are hydraulically driven, they are usually hydraulically driven, so that you have better control. They are smooth, so that it is all smooth, there is no sudden change. So, actually the wave sort of half wave rectification or full wave rectification we achieve with twin pump, and thus the delivery through which concrete will be actually delivered. All right. There are other kind of pumps which you will not look into, like peristatic pumps, which I think I will have to skip because of time constraints that we have. But there are other kind of pumps such as peristatic pumps, which are actually used in many laboratories, you might have seen, environmental laboratories. So, squeeze clit pump or peristatic pumps were used sometime, small pumps, but most commonly used is the hydraulically driven twin pump, same reciprocating type as I just showed, and they can be mobile boom pump. For example, it is like this. If you see this, is on a truck, it is on a truck, this is actually supported on the rigs, right, and this is a boom, and you can actually deliver anywhere you like, So, it is a mobile boom pump, it is a truck mounted on a truck and can be transported, the truck can come and you can just, the same pump is just simply on a, so it is on a mobile boom. So, you actually can deliver wherever it, wherever is required. So, that is a mobile boom pump, same one. Then you have got trailer mounted pump. So, for example, this is a trailer mounted pump. So, something like this is how it looks like, trailer mounted on the trailer on one side. So, this will be actually towed by other vehicle mounted on trailer, right, and you can see from the other direction. So, this is the form essentially meant for towing it off, and the pump is mounted there. So, you can have trailer mounted pump, or you can have pump which are truck mounted, and both are mobile. So, you can use them in conjunction with RMC. You can use them in conjunction with RMC very easily. You can use them in conjunction with RMC very easily. So, that is so far as the pumps are concerned. Pump performances, well, is for a 100 pipe, output per hour is a function of pumping pressure, and this will depend upon what is the length you are pumping through. So, at 200 meter length, the pressure required will be this much. For 25 meters, pressure required is less. So, as the length increases, length of pumping increases, pressure required will be high, and it is also function of higher the output, pressure required is high. So, this is one can understand pump performance from. So, therefore, the pump that you select would be based on what is the length one would like to pump, and what is the kind of output. So, based on this, pump capacity is actually selected. Then just we will come to the concrete a little bit later on, but pneumatic placers are used in some cases where actually it is the air, it is the air actually, air which compressed air which will be actually driving out the concrete. So, this is your pneumatic placer. So, you can see A is the casing, this A is the casing, this is the casing, B is the inlet hopper. So, B is the inlet hopper, this is the inlet hopper through which it comes. C is the bell shaped inlet through which actually your mortar or concrete etcetera will come, and D is the air entry, D is the air entry, this one is through the compressed air would enter, compressed air would enter, D is the air entry, and E is there is a nozzle through which also air will enter, D is the compressed air will enter through this nozzle, and F is the delivery pipe. So, your concrete enters from here, air under pressure, and it causes this to move. So, dry, relatively dry air makes quite often gunniting, for example, or similar sort of usage. You can actually one can use compressed air to drive the transport the cement mortar, or even concrete or grout or similar sort of situation. Not concrete dry, relatively dry, not grout really, relatively dry, but even grouts can be pneumatically placed through concrete. This is pneumatically placed through a pneumatically placed. So, this is not a very common thing, not in special cases only used. So, let us look at pumping and concrete flow. Now, we said that flows in form of a plug, that we have seen when we were talking about rheology of concrete. So, it flows in form of a plug, and we shall see a diagram of course, and there should be no relative velocity between aggregate particles, especially when your pipe is straight and you have constant cross section. So, for constant straight pipe and constant cross section, there should be no relative velocity between aggregate particles, otherwise there will be segregation, and concrete actually flows like plug. So, and the lubricating layer is there at the boundary. So, in other words, if you remember what we talked about, the velocity profile, it will look like this. There will be no velocity at the boundary, there is some velocity profile because there is a lubricating layer, but velocity profile. So, this is actually velocity V along the cross section, V P along this direction, H or cross section diameter, diameter. So, this is radius R and this is R. So, a little bit of velocity gradient at the boundary, but there will be no velocity here. So, it actually it is like this, actually it will be like this, constant, more or less constant. This has to be constant, but there is a lubricating layer there. We will just have a look at that in a minute's time. So, basically lubricating layer, and you should have no velocity gradient. So, lubricating layer, the path boundary is essential for pumpability, and that is important. So, compaction effect of pressure consolidated and forces grout out. Now, I said that it will be like this. So, there is a compaction, the concrete gets compressed from both the sides, concrete gets compressed because it is moving. the piston is causing it to move. So, piston causes it to compress, piston causes it to compress. So, when it compresses, the water will force out. So, grout comes out, in fact grout will compression, grout will force out. So, grout goes upward, grout forces out. So, compacting effect of pressure consolidates and forces out grout. So, material will come closer to each other, solid materials, and some grout will be forced out to the periphery. So, this is one action, this is one action, this is one action. Next thing is travelling action. So, when you travel a concrete, if you have seen that if you travel a concrete, this is your concrete, let us say, and you do travelling, you do some sort of travelling, just polish it. So, what happens? Travelling actually brings out vinegar water. Now, travelling effect occurs here between the pipe boundary and the grout, and the concrete itself. So, as it is moving, as the relative motion, pipe boundary is fixed, pipe is fixed, the material is moving, So, as it moves, there is a kind of travelling effect at the boundary, this frictional drag, due to the frictional drag, and that also pulls out the grout. So, this grout goes to the boundary, the compaction, also compacting effect of pressure also causes grout to move to the boundary of the pipe. So, the pipe boundary, if I have sufficient grouts available in the system, they will go out to the pipe boundary, they will go to the end of the pipe boundary and creates that lubricating, layer and create that lubricating layer, right. So, it will create those lubricating layer, and that is what it is. So, velocity here there is a reduction, but in this zone it is all constant. So, velocity is constant in this zone, this remains fixed concrete, this is actually the friction layer, the lubricating layer, the lubricating layer will be here, this is the pipe boundary. So, pipe boundary, pipe thickness, then the lubricating layer, and then the plug that would be there. So, flow is plug flow, the flow is plug flow, as we mentioned earlier, and you remember that was in the Bingham state, not 3, 4, just before 3 and 4. 1 is like solid, 1 to 2 like solid, 2 to 3 there is some kind of 2 to 3 is the plug sort of thing, and 3 to 4 was actually flowing like a liquid. So, here actually it should be best, it would be between 2 to 3. That means, it starts moving, you have a lubricating layer at the boundary, but the velocity, relative velocity between the particles within the plug is nearly 0. When we have sufficient mortar and which has got enough water and is sufficient to fill in the void. So, first of all you must have sufficient mortar in the aggregate system, and the mortar must have enough water and the fines which fills in the voids in the mortar itself, and slightly more. This will create a situation where lubricating layer will form readily, and this is set, the concrete in that case in the context of pumpability is called saturated. In saturated concrete, radial and axial pressure are same. That means, pressure in this direction and in this direction is same. There is pressure along this direction, uniform pressure in both transverse radial as well as in the in the horizontal or axial direction. So, they will be same pressure, all right. So, that is under saturated condition, because the grout would have moved to the boundary, formed a lubricating layer, and it is able to move. So, radial and this pressure will be same, and too much cohesiveness of course can result in too much cohesiveness due to excess cement and fines may prevent formation of lubricating layer. So, I must have a minimum fines content which should be sufficient to fill in the voids in the mortar system, or sufficient paste. I must have sufficient paste and slightly more then to fill in more than sufficient paste, which will obviously fill in the voids in the mortar sand system or aggregate system, but slightly more. In fact, you need more paste with lot more fines here. Fine means not fine aggregates, but fine are below say 300 micron or 150 micron. That sufficient fines should be there, so that my lubricating layer can form, because remember lubricating layer is formed because of the fine material present in the system, and cement and very fine part of the fine aggregate system forms this, and that should form that lubricating layer. So, I might have cement or cementitious material or some sort of inert fillers like limestone powder, or fly ash is of course a very good material for that purpose, because it is spherical in nature and it can fill in those, contribute to the paste content or grout content of the mix, and thereby actually it makes the concrete more or less easily makes it saturated, Now, good old days, there were no, when there were no fly ash and such things, people did test and they looked into say water cement ratio along this axis, water to cement along this axis, and the pressure, pumping pressure. So, it was observed that when you have low water to cement ratio such as this, your pumping pressure is very, very high. So, that we call it as 3, you can actually divide it into 3 zones. In the first zone, your pumping pressure is pretty high. This is actually unsaturated situation, because you have got less water, more of the solid, in the water to cement ratio is low, right. In other words, water to powder ratio is low. That means, water is not sufficient to fill in to make the paste flowable, right. So, I will not call it C today, I will call it cementitious, maybe CM, cementitious material. So, water to cementitious or powder, we might call it even powder. So, water to powders ratio, if it is low, it may be unsaturated. In other words, sufficient lubricating layer may not form because of lack of grout. There is a transition zone which is in between, where lubricating layer starts forming, and when water to powder ratio is sufficiently high, you have a saturated situation where lubricating layer readily forms and your pressure reduces down. So, it can flow at lower pressure, it can flow at lower pressure, it can flow at lower pressure. So, it is, if you see in another diagram, for example, the void content versus this side is a void and this side is a cement. Of course, I will call it powder here, current days we will call it powder, in good old days one would have called it cement. So, when you have got lot of voids in the system, high voids in the system and very little powder content, the voids will be remaining, and if you are trying to pump, it will actually cause segregation and choking. It is high void in the system, lesser powder material. So, it will actually cause segregation, or if you have too much of water in the system, it can even cause bleeding, right. It can cause bleeding. So, this zone is not very good for pumping, because you do not have sufficient powder in the system. It is actually the water goes out, it is actually the water tries to go out, and if the pores in the system, in the fresh concrete, pores in the systems are so fine that the water has got a it cannot filter out. So, if it wants to go out, it has to take the solid along with it, right. It it's not a it's kind of a reverse of a filter. In a filter, water goes out leaving the solids. Here, if the water has to go, it must take the solid in. So, water cannot go out, right. So, what should happen? The pores in the system must be sufficiently fine, very fine. And when can it happen? When you have fine particles, cement particles are sufficiently high, and this interstitial space between those cement particles is such that water just cannot move out through them, cannot squeeze out through them under the pumping pressure. This, if it happens that way, water will be going out, leaving the powder. Now, this can happen when you have too less particle or cement fine particle or powder system in it. So, water will go out, leaving the, so sufficient fines, sufficient powder or cement fines, I am talking of cement or similar sizes material. If they are there, they will ensure that the pore within them, interstitial pore within them is so fine, water cannot go out, they will have to take them together. If it is less, then there can be segregation, that is bleeding can occur, water may squeeze out. In between you can see that marginal, but somewhere you have, when you have a low voids in the system, low cement, it works out, it is readily pumpable, and is in this zone when there is compatible cement and the void in the system. So, void is, the packing is such, the system void in the system is sufficient, and cement is also sufficient to fill in those spaces. So, there is a compatible zone in which pumping does occur readily. But if you have too much of powder in the system, what will happen is, it will offer high resistance. Lubricating layer will form, but it will offer high resistance to actually flow because of too much of cohesion in the system. So, therefore, there is a zone of pumpability in between. So, it has to have very fine or powder material sufficient, right, sufficient powder material or appropriate optimal amount of powder material, which is more than the normal case. Normal, it will have more paste in fact and flowing paste, but not excess water, just flowing paste, sufficiently flowing paste. So, that paste flows and it takes the aggregate also with it. So, water goes, it must take the cement with it and the powder, other powdery material with it. So, that paste moves as a single entity and embedded aggregate also moves. So, you will have slightly higher paste content in pumpable concrete. Now, people have tried to relate this to slump, and if you see in this particular diagram, slump increases along this direction, slump increases along this direction. So, slump is here, more slump here, and this is the pumping pressure. So, about 130 mm slump, here it is 130, pumping pressure is very small. Pumping pressure increases parabolically depending upon of course, the aggregate size, aggregate size, smaller size aggregate, larger size aggregate, etc., etc. So, pumping pressure increases as the slump reduces. So, one can say that somewhere around 120, 130 mm of slump, concrete will be pumpable. But remember, slump is one thing, amount of fines is also important. So, I can achieve this slump of course, with the admixture, but also amount of fines must be sufficient, otherwise there could be choking. So, slump is an important thing, right. So, most of the time we actually define slump for pumpable concrete as 120 plus, maybe 130, 140, 150. In fact, IS 456 2000 also gives you the minimum slump required for pumpable concrete, somewhere around 100 or 120, I do not remember exactly, not really at the moment we are interested in that. But the fine contents, if I look at cement content in good old days, this I can call it as powder content along this axis. So, if I increase my powder content, there is an optimal point. Beyond this, if I increase my powder too much, the pumping pressure, this axis is pumping pressure. So, pumping pressure will increase if I increase, it will increase, and low cement or low fines, pumping pressure is also high, it reduces as I increase and further. So, I have an optimal quantity of the material. Which material? The powdery material, which will give me least pressure, like we mentioned earlier, right, least pressure we mentioned earlier. So, that is it. So, we should have optimal fine content. So, pumpability, one must look at the optimal fine content. Similarly, one can look at the aggregate content. This will also give us, since the fine content has to be, powder content has to be optimal, correspondingly aggregate content is also optimal. So, you have got an optimal. If you have too much of aggregate, less powder, it will be not pumpable, pressure will be high, and when you have too less of aggregate system, so then also again pumping pressure will be high, right. And then let us look at, this is related to coarse aggregate content, similar sort of situation. Here coarse aggregate content is lower here, higher on this side, lower on this side, high on this side. So, lower on this side, actually you will find that it is something similar concept. So, I think I will skip this quickly because we have something more to look into. So, if it is saturated concrete, in fact, the pressure at any point at distance x, pressure at any distance x can be, pressure at any distance x can be related to P 0 is the pressure, P is the pressure at distance x, P 0 is the delivery end, d I is the particle, d I is the pipe diameter, and r is flow resistance per unit area of the pipe. So, pressure at any distance from the delivery end, at x distance from the delivery end, one can relate like this. In other words, you can find out if the P 0 is known, if the pipe diameter is known and resistance, flow resistance per unit area of the pipe is known, which will be a function of the mix, then one can find out what is a maximum pumping distance. So, x max will be given by simply x max you can obtain by P 0 d I by 4 r. So, one can actually get, because when P is equals to 0, you can find out what is the value of x, that is the x max. For unsaturated concrete, there is one formula like that, but that is more complex, a little bit more complex. You have a coefficient of friction between concrete and the pipe coming in, and also coming in adhesive resistance similar to yield stress, radial pressure to axial pressure ratio, because radial pressure to axial pressure were same, mu k coming in here, it was same before, it was 1 earlier, and this is the kind of formula. So, it is actually exponentially reduces, right, and this is the kind of formula. This A is a something adhesive resistance similar to yield stress. So, that is more complicated, but saturated concrete is what is desirable, right, and this fraction, friction or the force, the R resistance offered is a function of the concrete type, and saturated concrete will have, is you can pump more through the saturated concrete, right. So, therefore, x max you can find out even in this case given by this formula d I over 4 mu k ln. You can simply put a P 0 equals to 0 and put P equals to 0, you will get an expression for x max given by this. Simple algebra, there is no problem, put this equals to 0. So, this is this minus this, take it on to the other side, take ln of both sides. So, it will become simply 4 mu k x by d I and ln P 0 plus this. So, you can actually get an expression, and this will be simply ln of all of those things. So, you can actually obtain an expression for this particular one, right. So, in fact, this will be separated out. If you put this equals to 0, this goes to the other side, multiply by mu k. So, you can separate this out, and simple algebra will give you this formula. I do not think I will derive this, it is very simple, and one can do this. Pressure bleed test is the one test which is used for pumpability. Now, this equipment looks like this. You have a kind of a tap here, bleed tap. There is a kind of a there is a kind of a mesh here. There is a kind of a mesh, right? A mesh here, standard mesh. Here is the concrete, and there is a piston through which you apply a standard pressure. So, apply standard pressure, and after you apply the pressure, there is a mesh here which allow water to pass, but no solid. So, bleeding will, under this pressure bleeding will occur. You measure the rate of bleeding or volume, that is the water that is actually accumulated at 10 seconds to 140 seconds, and pumpability is related to this pressure bleed test. In the x axis you have actually the V 140 minus V 10, that is the volume of water that comes out. So, if the water comes out over a longer period of time, initially if it goes out first 10 minutes past 10 seconds is actually omitted out, and it should come out in a slower speed. So, pumpability is readily defined depending upon slump. This axis you have slump, this line. So, this is the zone of pumpability, readily pumpable zone, where I have got sufficient value of V 140 minus 10, this value is high, and slump is corresponding to the slump. So, both slump and pressure bleed test can be used together in order to obtain the pumpability. So, this zone is readily pumpable. Of course, it is not a very popular test, most of the people use slump, and therefore, not necessarily always high slump will ensure you pumpability. Well, just to conclude our discussion, effect on pumping of concrete, dry air consistency, it tends to become dry. No negative effect, actually increase in temperature slightly because of the friction, slight increase in air content, and no change in strength or shrinkage, although aluminum pipes may cause loss of strength. If it is just aluminum pipe without any coating, because aluminum can react with concrete, calcium hydroxide and all that, aluminum can react actually the concrete. C3A system, aluminate system can react with also concrete. Lastly, some do's and don'ts with concrete to end our discussion on transportation and all. For example, this diagram shows if it is a small mixture, you should actually load full load should be put onto the barrow, full load should be put onto the barrow, full load should be put onto the barrow. Unlike in this case, this is not the best thing to do, this is not desirable. Half load onto the barrow, half load on another barrow. This will have a stony batch, this will have more paste, more mortar. It should be full load should be put on a barrow, right, because this sort of mixture machine will have a tendency to discharge larger particle in the beginning and finer particle at the end. Now, again this is not desirable, I mentioned yesterday, this kind of a discharge is not desirable, neither this, one thing is narrow and inclined. It should be actually desirable is a direct and then through a bottom opening large bucket, large bottom opening bucket, and this is not, again this if you discharge, stones will come here, mortar will come there. So, narrow opening, very little will come here, stones will come here, mortar will come here. Here the paste will have a tendency to come, aggregate will remain. Large bottom opening is always better, this is not good, this is not good. Yesterday last lecture also I mentioned same, large bottom opening is better. Dropping directly through a height is not desirable from a conveyor belt, for example, you might drop it through kind of chutes or guides. So, this is also just to kind of strengthen our discussion which we had earlier, right. So, dropping of concrete, some do's and don'ts with concrete handling related to manual handling. So, I think with this we conclude our discussion on this particular lecture, the third lecture of the fifth module. We talked of workability, we talked of empirical measures of workability, then we looked at pumping. Next lecture we will look at compaction and curing. Thank you very much.